All right.
How did you also?
I don't know.
You didn't go?
Mm-mm. Did you go? Oh yeah, that's right. You didn't. I heard everyone bombed. No one practiced. No one watched the videos I put up explaining.
We got 7. She's the only one from Bros that placed.
Have y'all done this? I handed it back to y'all to correct. So I only have one student. The assigning oxidation numbers. Because I told y'all there was issues with the back. Do y'all need to correct? Y'all need to get it done and turned in. Where's my sheet? So, acetate. Acetate is a common ion. It has the formula that's usually written as CH3, COO negative. You can combine them all together. It's usually written this way because this single oxygen has an additional electron on it, making it negative. So anything that bonds to this ion is going to bond on this oxygen, and thus it's usually written this way to indicate that the one oxygen is going to be what's bonded. It's a carbon in the central with another carbon. Actually, pull up and show you a three-dimensional. So it looks like this. We have a carbon and a carbon. One of the carbons has 3 hydrogen. And then 1 oxygen. And then this oxygen has an additional electron, making it negative. It's a ion. So the most common form of acetate that you encounter is acetic acid. So what would the formula for acetic acid be? What does it mean to be an acid? H plus, so we're adding a hydrogen cation. So it's an H plus cation with acetate anion. And these are combined together. Acetic acid is written weird. Anything with acetate is usually written weird. The formula, the most common formula, so this is 1-to-1 ratio. The common way to write it is CH3COOH. Why is this formula weird? So one thing is that there's 2 carbons, so you could have combined it like this. But and what's another weird thing about it? No, there's not a hydroxide at the end. So let's think of table salt. NaCl. We have Na plus and Cl negative as the 2 ions. What's our 2 ions here? CH3COO negative and H plus. Almost always when writing ionic formulas, we put the cation first in the formula. So this is usually how it's written. But by convention, we usually also write it like this. Putting the cation by what we use by convention in the front. Another way is to use the more empirical formula, HC2H3O2, where this is again the alternative way of writing acetate ion with the cation in the front. And sometimes you'll even see C2H4O2. Out of all of them, this one I hate the most, because this is an ionic formula. You should break up the cation and the anion. So drawing this, and we see C bonded to an H, bonded to another H, bonded to another H, bonded to another carbon. There's a double bond on the oxygen. There's an O that has an additional electron to balance it out with an H. So this is acetic acid. What's another name for acetic acid? What's the common name? Does anyone know? Does anyone know what the common name of acetic acid is? You have it at your house, most likely. You cook with it. Vinegar. It's vinegar. I'm trying to think of the best way. I'm going to stick with this formula. Even though this one is more commonly used. The reason why I'm sticking with this one is that we can clearly see by convention, we always put H plus in the front. And regardless of what form that acetate uses, the anion is at the end. You could either have it like that, or HC2H3O2, like this. One of these two. So, in elementary, you should have done this before. You should have made the chemical reaction between vinegar which is CH3, COO, and what else? In elementary, what chemical reaction did I use using vinegar? Baking soda. Did y'all do that in elementary? That's a common thing they usually do in elementary. Or at least junior high science portion. So what is baking soda and acid? Close. So soda is the short word for sodium. And you're right with carbonate, but it's not carbonate, it's bicarbonate. Bi meaning it has additional hydrogen. So what's the equation for sodium bicarbonate? And A is our cation. And our anion would be, well, we know it's carbonate. So carbonate is CO3 2 negative. And we're going to add a hydrogen, because that's the bi. And hydrogen is positive, which turns that into just a negative. Plus and negative is a 1-to-1 ratio. So it's Na HCO3. So what's the equation? What do we get? So we're going to take HC3COO and we're going to react it. By the way, vinegar. Does vinegar dissolve in water? Have y'all never looked at a bottle of vinegar? What did I say about acids? Assume almost all acids dissolve in water. Looking at our solubility rules nonetheless, and it's not inclusive, but we can assume all acids. So, if it has the cation, acetate, there's no exceptions, it will always dissolve in water. So, make that aqueous. Baking soda, NaHCO3. Does that dissolve in water? Well, coming over to CO3. Let's see, solubility, just to confirm. So it says, even though it doesn't say hydrogen, the bi portion of it doesn't really change its solubility or anything. But it says the exception is with an alkali metal. Is sodium an alkali metal? So it's a carbonate with a, you can ignore the additional hydrogen. It's carbonate with sodium. So sodium is an alkali metal, so that means an exception. That means it's not. That means it is soluble in water. So this would be aqueous. So we have. That one's most definitely dead. So we have HCH3. It's an acid. Acids are almost always soluble in water. And we have NaHCO3, which can dissolve in water. And what does it make? So this one's going to be weird. So remember the volcano experiment. What do we see being made? What was one of the things it does? So a gas is coming out. What gas do you think that would be? Hydrogen, oxygen, or something else?
Carbon dioxide.
Carbon dioxide. So we go have a CO2, which is a gas. One of the few chemicals you have to remember what it is. This one's more complicated than I wanted to do. I'll go ahead and tell you it makes H2O, which is a liquid. And let's see, what's the best way of doing this? So if we assume that this is double displacement, we'd see the sodium is going to mix with this and make sodium acetate. Which is very soluble in water. That's that thing where I put a crystal in it and it instantly solidified. I made a super saturated solution of it. And this, mixing with this, gives us H2CO3, which isn't a thing. Hydrogen carbonate is unstable, in which case we can break out of this an H2O and a CO2. I haven't gone, that's where this comes from. I haven't gone over determining whether or not this is stable. But if you do double displacement rules at least, you would see that swapping this anion with that cation, this anion with that cation, you would get sodium acetate and this, but this quickly breaks apart into water and CO2. The important thing is not getting this equation yet. The important thing is how much sodium bicarbonate, do we need to mix with vinegar to do this reaction? How many grams of baking soda per grams or volume of vinegar do we need? First of all, is this balanced? How many hydrogen do I have on the left? 1, 4, 5. How many do I have on the right? 3, 4, 5. How many carbon do I have? 1, 2, 3. How many carbon do I have over here? 1, 2, 3. How many oxygen do I have? 1, 2, 3, 4, 5. How many oxygen do I have over here? 1, 2, 3, 4, 5. It is indeed balanced. Same number of hydrogen, same number of carbon, same number of oxygen. So that means one molecule of vinegar, sodium acetate, reacts with, that's your plus sign, one molecule of sodium carbonate to make, that's the arrow, one molecule of sodium acetate and one molecule of water and one molecule of CO2 gas. So this is what this entire equation tells you. If we take one molecule of vinegar and react it with one molecule of sodium bicarbonate, we get one molecule of sodium acetate and one molecule of water and one molecule of CO2. I don't know about y'all, but do y'all like doing chemistry where you actually use one atom at a time? Like if you were to go in the lab, would you literally take one molecule of water and try to do that? What's something more useful? But it's still counting number. So because atoms and molecules are so small, let's jump this up to 6.022 times 10 to the 23 molecules, which is called 1 mole. Right? So another way of saying that is we can increase this to 1 mole of this, reacts with 1 mole of this, to make 1 mole of this, and 1 mole of this, and 1 mole of this. So it's a 1-to-1 ratio in the terms of number of molecules. 1 molecule of this and 1 molecule of this react together are 1 mole of this if we want to increase them out with 1 mole of this. But when we go into a lab, we cannot measure 6.022 times 10 to the 23 molecules directly. So let's figure out what is the molar mass of HCH3CO, acetic acid. So there are 4 hydrogen, 2 carbon, and 2 oxygen. So that's 4 times 1.00794. 2 carbon. Carbon is 12.0007, I think. 12.0107. And 2 oxygen, this is the 15.9994. So adding that up, the molar mass is 60.05196 grams of acetic acid per 1 mole of acetic acid. That's the molar mass. Our next chemical, molar mass of sodium bicarbonate. So there is 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygen. So 22.98977, 1.00794, 12.0107, and then 3 times the 15.9994. Adding up all those. I get 84.00661 grams NaHCO3 per 1 mole of NaHCO3. So if I have pure vinegar, I want to do it at this ratio. Approximating, I want to do 60 parts vinegar to 84 parts sodium bicarbonate baking soda. That is my ratio. What would happen if I use 1 billion tons of vinegar to 84 grams of sodium bicarbonate? So if I'm doing how does it differ from 60 grams vinegar, pure vinegar, with 84 grams of baking soda? How does this equation change if I change 60 grams to a billion tons? How does the result change? That's all it would be, is leftover vinegar. The overall reaction doesn't really change. I would get the exact same amount. I would get the exact same amount of carbon dioxide, the exact same amount of water, and the exact same amount of sodium acetate. The only thing different is I would have a lot of vinegar in excess. So it's important to, when doing chemistry, to realize what if something is in excess or not. And sometimes you want things to be in excess and you're trying to make something. One of the key things, if you ever watch chemistry videos, there's a YouTuber called Nile Red. I highly recommend watching him. He's an entertaining and good person. But you'll see when he goes through all the reactions and stuff, he keeps track of what the theoretical yield should be. And at the end of the vehicle, he usually comments, I got 53 grams, but the theoretical amount was 100 grams. He should have got 100 grams. So that means he had a 53% yield. That means they lost 47 grams that he was unable to recover. If you're doing any sort of chemistry, like at your house or on your own, you're going to find out that chemistry in the real world is extremely difficult. I've seen YouTubers who are like go on and show reactions, say that have gone back and attempted reactions that they couldn't do 5 years ago, just because over 5 years of making YouTube videos, they've grown as a chemist. Some reactions are notoriously difficult to pull off. As you basically are trying to, again, get one molecule to react with another molecule. And you have to do it in certain ratios, and your result is going to be you're going to have some excess of a chemical left over. Now that excess is that vinegar is an acid. It can react with a whole bunch of other stuff. And this is just showing one line. But here's a question. If I mix 100 grams of pure vinegar with 100 grams of baking soda, how much sodium acetate and CO2 gas is produced. So we know that there is going to be one chemical in excess and one chemical that's not. There's always going to be one, unless you have a perfect 1-to-1 ratio, like the perfect amount, one thing's going to be always in excess. So in this equation, what would be in excess? So we know the ratio is 60 parts this, and or 60 grams to 84 grams. And I'm rounding. So if I were to keep adding more and more to each of these, which one would reach 100 first? Baking soda. And if I were to increase keeping the ratio the same, so the ratio is 60 to 84, and if I were to increase the 84 to 100, what would be the top number? So basically cross multiply, right? So 60 times 100. This is related. Y'all should have done this in first algebra, or if not before that. To 84x, solve for x. You would see that our x is 71.43 grams. So if I increase the baking soda to 100 grams, then only 71.43 grams will react. Does that make sense? So, that means that we have an excess of about 29.5 grams. Because the ratio is always going to be the 60 to 84 ratio. If I put 1 billion tons of this, it doesn't matter. Only 71.43 grams will react with 100 grams. Only 60 grams will react with 84 grams. So no matter, so this is called being excess. No matter how much vinegar I use, only 71.43 grams of vinegar will react with 100 grams of baking soda.
So if we did those exact numbers, since vinegar is aqueous, would it dissolve in the water produced from the reaction?
Repeat that?
If we used both 100 grams and there was excess vinegar, since the reaction produces water and vinegar is aqueous,
yes,
the water produced dissolved in vinegar, that is excess?
So first, you can't really have 100% vinegar. I'm trying to not get ultra complicated. We're going to learn what happens when you have 4% vinegar mixed with 5 molar acid, or base. But I'm trying to assume everything's 100% right now, making it easy. There's also, there's also only so much can dissolve in water, the exception being acid. Acids you can dissolve 100% of acid into 1 drop. It's more accurately calling it diluting the acid. You think of more of you're dissolving the 1 drop of water in the acid from the other way, but you would maybe just diluting the acid is the more correct way. We treat acids as they're dissolving in water, but more accurately, you're diluting the acid by watering it down. Acids are weird. You can assume every acid we'll cover in this class is aqueous. that dissociates into ions in water. But anyway, we call the vinegar here the excess, and the sodium bicarbonate the limiting reactant. It is limiting how much of the vinegar will work because we're at the max. Another little trick, by the way, let's assume wrong. Let's assume that you guessed that baking soda was an excess. So I'm going to assume that I can convert the vinegar to 100 grams. What would the X be here? Again, cross multiplying, I see 60 times X, and then 84 times 100, divide by 60 on both sides. And I see that the number of baking soda that I need is 140 grams. So the ratio here is 100 grams vinegar is equivalent to 140 grams of baking soda. But my question says I have 100 grams of vinegar and 100 grams of baking soda. You can see that I'm trying to use more baking soda than I have allowed. So this is impossible, what means I guessed wrong on what was in excess. What was in excess is the vinegar. So I'm assuming I'm using 100 grams of baking soda, which means that only a certain portion of the vinegar is going to actually react. So you'll also find in the real world, this theoretical thing is always true. The reason why is complicated. Sometimes so when you're putting sugar into like tea, you can look up the theoretical amount of what can dissolve into the sugar, but you know that it doesn't instantly all dissolve. You have to stir it. And as the longer and longer you stir it, the more dissolves will happen. But theoretically, you need to stir it for like an infinite amount of time in order to get every molecule to fully dissolve. Thus, to get every single molecule of this acid to dissolve with this powder will take almost a long time to get every single molecule to react. And so what you're going to end up happening is some of the molecules will be at the bottom and not reacting with the top. And we don't get perfect results and perfect yields. But that's irrelevant. We're going to assume everything's theoretical. So what this tells us is we're going to get an extra amount of vinegar at the end. We're going to mix 71.3 grams. So regardless of the fact that we're using 100 grams of vinegar, only this amount is reacting. All of the baking soda should fully react. And we're going to get sodium acetate, some water, and some CO2. Now we know the ratio is 1 mole of this to 1 mole of this to 1 mole of this to 1 mole of that, or 1 mole of this. We also know the ratio is about 60 grams of this to 84 grams of this. And to find out what this is, again, this is the molar mass. It's 84 grams per mole. So we need to figure out the molar mass of this. So the molar mass of Na would be, so 1 sodium. Sodium is 22.98977. 1 carbon, 12.0107. 3 hydrogen. And 2 oxygen. So the molar mass is 70.02309 grams NaCH3 to 1 mole of NaCH3OO. There's another carbon in there. So we have a ratio here too. 70 grams about. So we can use related ratios to solve this problem. And that's mostly what this is. So if it's 84 grams, gives us 70 grams of this. And if we're going to use 100 grams of baking soda, what would be the amount of sodium acetate we get? And again, it's just cross multiply. 84 times x equal to 100 times 70. 84 is being multiplied on that side, so I divide on the other. I will produce 83.3 grams of sodium acetate. So mixing 100 grams with 100 grams, I get 83.3 grams of that. And finding out the molar mass of CO2, it's 1 carbon and 2 oxygen. That's 44. I'm also rounding for brevity. So the ratio over here. So these top numbers represent if I'm using exactly 1 gram, or 1 mole, I mean. So 1 mole is 60 grams, 1 mole is 84 grams, 1 mole is 70 grams, 1 mole of this would be 44 grams. And I can use, and the bottom numbers is what we're actually using. Does that make sense? So 1 mole is equivalent to, and it doesn't matter which one you use, I'm going to use this one, is 84 grams. And 1 mole is 44 grams, roughly. But I'm using, actually, so it's 1 mole is 84 grams, but I'm actually using 100 grams. 1 mole of this is 44 grams, but I'm actually using X number of grams. So solve with the X of how much CO2 is produced. I cross multiply. So 84 times X is equal to 44 times 100. So X is equal to 44 times 100 divided by 84. And I will make 52.38 grams. I'm going to go ahead and guesstimate the water real quick as I'm running out of time. I know water is 18 grams per mole. So doing water, that's 84 to 100 is equal to 18 to X. So that would be X is equal to 18 times 100 divided by 84. 21.43 grams. So doing this reaction, and also technically you would have, I forget, you would also have an excess vinegar. You would still have vinegar on the right hand side. It'd be 100 minus that number, because it was an excess. So this was unused. So doing this reaction, this is what I would see at the very end. I should expect 83.3 grams of sodium acetate. about 21.43 grams of that, and I will produce 52.38 grams of carbon dioxide. This is why this produces a lot of gas. We produce a lot more grams of carbon dioxide than water. And this is why this experiment is so famous, is because it produces a lot of CO2. So for every 171.43 grams, 52 grams of CO2 is produced. What ratio is that? So 30% of the mass, the input mass, turns into CO2. Make sense? We're running out of time, but this is basically what we're going to be doing next. It's almost identical to what we just did, except for now we're going to be actually analyzing the equations and using them. Making predictions. I want to do one more example, but it took all class period just to do this one. So that'll be it for today. That one was very easy, as it was 1 to 1 to 1 to 1 to 1 ratio. When we have coefficients, it's going to change up slightly. And you have to keep track of the coefficients, as it's now going to be 2 moles